Welcome once again to MET 4112, Computer-Aided Engineering and Analysis. I'm Dr. Kenton Fleming, and for the last couple of classes, we've been in a series of studies involving mesh refinement in CFD, Computational Fluid Dynamics. And we started the study of mesh control with the assembly file called ejector in exhaust hood. So let's review a little bit of that. And what we had to do, we created a study, and it was a two-constituent flow, if you recall. It had chlorine and air in it. We created a new configuration. We used USA units. We had an internal flow with exclude cavities without flow conditions checked. We included gravity. We included air and chlorine. Set the defaults. We began our initial conditions with 100% air and 0% chlorine in the exhaust hood chamber, and we accepted defaults for mesh. Now we went to the flow simulation analysis tree, and we created our boundary conditions. And as you recall from the last video, there was a discussion on how to select surfaces that are difficult to select. We had to select a surface on the other side of this. The way I do this is I just section the view like so and hide my computational domain, and I also hide this global coordinate system here. Go to ejector analysis, hide global coordinate system, and there I have now I can reach inside the chamber and select my boundary conditions. The boundary conditions, as you recall, the I inserted a pressure and environment pressure boundary condition. We have the default standard temperature and pressure, and it looked like this. And then I selected a boundary condition, or inserted a boundary condition, that was an outlet volume flow of 1,000 cubic feet per minute. Alright, right there. And then, as you recall, we examined some things about our initial mesh. We looked at the minimum gap specification, or the manual specification of the minimum gap size. We checked to expose what was automatically generated, 1/2 foot, and we remembered that came from selecting our boundary conditions, and the smallest fluid flow passage in those boundary conditions was selected as the minimum gap size. What minimum gap size means, as we review, was that it's the smallest flow channel in the computational domain that SOLIDWORKS sees, and it sees these things as you specify boundary conditions. As you recall also, the problem statement here is resolving this very small injector nozzle surface area in the overall computational domain, which is much smaller than other flow channels and the overall computational domain size. Then that we discussed that by resolving this, we would also too excessively resolve with too many mesh elements of too small size inside the rest of the domain, and how to control that. Alright, so we specified this boundary condition then of chlorine gas as an inlet volume flow at this injector nozzle, like so, of, if you recall, 0.14 cubic feet per minute. .14 cubic feet per minute. And there we have this. And then finally, as a sort of a type of boundary condition, if you will, a flow simulation, insert porous media. We selected the screen material, and the screen material is a user-defined, or is a predefined material that will allow these solid models of the surface here and the top surface here to act as screens, so that flow can pass through those. That is a type of boundary condition. Okay. And then we went back to examine our initial mesh, input initial mesh, to see what the minimum gap size was after we specified the injector nozzle boundary condition. And you can see that SOLIDWORKS is trying to define a minimum gap size as 0.0003 feet. And that's going to resolve this nozzle, but it's also going to excessively resolve the rest of the computational domain. And so what we did was we said, let's let this gap here be the minimum gap size, and we'll specify it manually. So I'm going to do that right now, again in review, initial mesh, and do a manual specification of the minimum gap size of 0.067. That was about the width of those spaces through the baffles. And also going to do the same for the wall thickness, because the wall thickness is like the gap size, but refers to minimum solid thicknesses encountered in the computational domain. And since SOLIDWORKS flow simulation likes to split cells between fluid and solid regions, we give this the same specification. Alright, I want to leave these as the default right now. And then what we did was we created a mesh. We ran the simulation without solving the differential equations of fluid flow, just the mesh. And we got that. Alright, now after solving the mesh, we insert a cut plot on the plane that is centerline, named centerline, and that's what we get, something that looks like this. If we look at it from the left view, that's a decent mesh. But now, as you see, there's not enough. There's even less than one cell covering the injector nozzle surface area right there, as you can see. Now, so what do we do here? We still have not resolved this. Now let's go and show the cut plot once again. Alright, let's look at this. Let's zoom into here, and what we see is part of 1, 2, 3, 4, and part of another one. Really 4 cells, but we have a non-symmetric solution or distribution of cells here. We'll cover that in the next video. Welcome once again to MET 4112, Computer Aided Engineering and Analysis. I'm Dr. Kenton Fleming, and we have been studying a series of lessons on mesh refinement in computational fluid dynamics in the geometric domain of an internal flow problem for this application of an ejector and exhaust hood assembly. Now, as you recall, last time we had to create mesh controls of local initial mesh such that we could refine the inlet flow geometry without over-refining the geometry elsewhere. And we used a couple of tools to do that. We used the initial mesh and the narrow channel refinement, and we also used the local initial mesh, refining all cells. We use the local initial mesh, refining all cells, to finally refine the cells in the local initial mesh around this area right here, the injector flow nozzle. Now what we need to do today is study how do we modify the distribution of these cells such that they are placed more centrally across the diameter of the injector nozzle. Now, as you can see, those 4 cells are distributed evenly, as the basic mesh elements are distributed symmetrically about the nozzle. There you go. Now finally, we need to resolve the same, like we did here with the local initial mesh on the surface area. We must refine using a local initial mesh on this volume of the computational domain right in here, because I have chlorine gas coming in through here like so. And I want to make sure I have enough cells that will resolve the boundaries between the chlorine gas stream and the air that's inside of this cavity. I don't have enough cells right now. Now I have completed the solution for the mesh, and I'm solving here, seeing about 100,000 or a little over 100,000 mesh elements. Let me close this, expose or show the cut plot again, and let's see what we have. See, we have a lot more refinement in here, and you're going to find that to be quite favorable when we solve this problem now, because we're going to have a thin, narrow stream of chlorine coming up through this hood, out through this porous media, and into this area out here, through the baffles, and out the exhaust of the exhaust hood. To review what we've discussed today is the redistribution of cells using the plane control dialog in the initial mesh, the basic mesh by adding planes or editing the location of planes through here. We have also introduced the use of local initial mesh by applying the mesh parameters in a local initial mesh to a complete solid component, thus affecting the mesh inside the component's volume. Whereas in the previous lesson we applied the local initial mesh 1 to affect or influence the mesh across a surface area. Now the next thing I'm going to do is solve this flow, and I'm going to do so and show you the results of what this thing looks like. Okay, now the flow is finished. It took 16 minutes to compute in CPU time. It performed 240 iterations, and typical iteration took about 5 seconds. And we look at the preview window here. So I have two cut plots being displayed, one for the concentration contours and one for the velocity vectors. And you see the velocity vectors kind of aligning themselves with the airflow and the chlorine flow. The air comes in here at a small velocity. Keep in mind, it's probably a large flow rate since we're pumping in 1,000 cubic feet per minute over a large surface area right here. Now, and that's the flow solution. Pretty interesting problem. We have a little bit of flow coming through the under baffle there. That's the solution to the flow field at the center plane. Of course, you can look at it at other planes as well. But this concludes our lesson of solving flow in a multi-constituent flow chamber called the ejector and exhaust hood assembly, where we had to use several means at our disposal to control the mesh in this computational domain.